So good evening, friends. The topic for today is extremely important. I will cover the 5 topics: the normality issues in SmartPLS, then internal consistency reliability measured by Cronbach alpha, the multicollinearity, and multicollinearity is measured by variance inflation factor. So what is multicollinearity? I will explain. Construct validity. There are 2 types of validity: convergent, discriminant, and the biasness. So these are the 5 issues which you have to check before going to the hypothesis testing. And discussing these issues is almost important whether you are preparing for a thesis or you are writing a paper, because you can get the queries on any of the aspect. So the topic for today is this. So first of all, let me talk about the normality, because there are a lot of confusions in normality. There are different type of normality: univariate, multivariate. Then measuring the normality issues. Normally, we examine the normality by looking either the skewness and kurtosis or Kolmogorov-Smirnov test. If your data is collected from questionnaire and you are using the scale variable, your variables are measured on 5-point scale, 7-point scale. So ideally, you should not go for Kolmogorov-Smirnov test. The skewness and kurtosis is enough. And it is mentioned that the skewness and kurtosis are of 3 levels: 0, less than 0.5, less than 1, and more than 1. And there's a lot of confusion in skewness and kurtosis, because some scholars say me that we have read in the books that the limits are plus minus 2. So, and in papers it is mentioned that plus minus 1. So what is the correct answer of that? So basically, when you are calculating the value of skewness and kurtosis, the ideal value is 3. But if you calculate manually, but all these softwares considering 3 as a 0. So they are giving you the adjusted value of skewness and kurtosis. So when you are calculating it manually, so in all the old papers, it is given with respect to 3. And with respect to 3, so the answer is different. You can consider 2. But when you calculate from the software is giving with respect to 0. Whether you are calculating from SPSS or MOS or PLS, the 0 is the ideal value. So it is called adjusted skewness and kurtosis. So the software is giving you with respect to 0. If it is 0, it means there is no skewness problem and no kurtosis problem. If it is less than 0.5, it means negligible. If it is less than 1, then we can say that it is fine. It is near to the normal. We cannot say it is perfectly normal, but we can say it is near to the normal. And if it is more than 1, then it means it is away from the normal. So the reference I will show you, I take this from the book written by Ringel. And it is mentioned that it is plus 1 or minus 1. So a general guideline for skewness is that if the number is greater than plus 1 or lower than minus 1, this is indication of substantially skewed distribution. For example, for kurtosis, the general guideline is that if the number is greater than plus 1, the distribution is 2-peaked. So benchmark is basically the 1. And 0 is the ideal point, right? So this paragraph I take from the book. So according to me, from many references, I found that If your skewness and kurtosis is less than 1, so you can say my distribution is near to the normal. Especially when you are measuring the variables, measuring the statements on 5-point scale or 7-point scale. In that case, you have to compare with 1. And in some of the, especially covariance-based SAM, they are also calculating the multivariate normality. Multivariate normality means taking all variables together. So taking all variables together, whether the construct or the model is having multivariate normality or not. Multivariate normality is measured by Mardia coefficient of kurtosis. And the Mardia coefficient of kurtosis, ideally, it should be less than the number of statements. Suppose you are having 50 statements in the model. So Mardia coefficient of kurtosis should be less than 50. This is the ideal value of Mardia coefficient of kurtosis. However, there is no literature available about Mardia coefficient of kurtosis, which is saying some standardized value. But from mathematical point of view, we know that the Mardia coefficient of kurtosis should be ideally less than the number of statements in the model. So I have shown you the paragraph also. Now with respect to covariance based SAM, it is almost mandatory that your model must have univariate normality as well as multivariate normality. And if your model is not satisfying this condition, your goodness of it will be very, very bad. It will negatively impact the goodness of fit measures or statistical fitness measures. In case of SmartPLS, because we are not calculating the goodness of fit, and even if the data is not normal, it is allowed. SAMPLS model is allowed. And in order to remove the problem of normality, you are having the facility of bootstrapping. So you can run the bootstrap SAM or bootstrap PLS. Both you can do. So bootstrap is a process where the small data set is converted into a large data set by replacement. And after some time, when your model becomes, when your data becomes normal, then the software calculate the values. So it is a kind of sampling distribution. So you pick many samples from a single sample. So in SmartPLS, we are having the value of 5,000. Software will take the 5,000 samples and calculate the value and give you the average. So that average seems to be near to the parametric. So whenever somebody asks you that how you adjust normality in PLS, the answer is bootstrap algorithm. The PLS software is providing you the bootstrap algorithm to adjust the non-normal distribution. But you are allowed to apply the model even if your data is not normal. The second condition which is coming is about the Cronbach alpha. So let me discuss one by one, and then I will show you how we can tackle with this. Internal consistency is related to the relation between the items in a construct. When you are using a construct and the construct is having suppose 5 items, 4 items, or 6 statements, 4 statement, 5 statement. So we want to know that how much these items are related to each other. So we assume that whenever we are measuring the construct from the items, for example, this is a construct and it is measured by the statements. So we assume that all these statements are highly correlated, especially when it is reflective in nature. So this relationship between the items is known as Cronbach alpha. So Cronbach alpha, this is the formula for Cronbach alpha. If you see the formula, the Cronbach alpha is calculated from two input. Number one, what is the average correlation between the items? And the n is the number of items in the construct. So if you see more carefully, higher the n, more is the alpha. Higher the r, more is the alpha. So Cronbach alpha is directly related to the n and r. So your Cronbach alpha is influenced by two inputs, number of statement. If your construct have more statement, then Cronbach alpha is found to be high. If you have high correlation between the constructs, between the items in a construct, Cronbach alpha will be very, very high. So ideally, we should not have more than 7 statement in a construct. Otherwise, the Cronbach alpha will be very, very high. And if there is a high correlation between the items, then Cronbach alpha will be very, very high. So this formula will help you in understanding the concept of Cronbach alpha. Let me tell you one thing very clearly. This Cronbach alpha should be between 0.7 and 0.9. 0.7 and 0.9. Because if it is more than 0.9, then it means it is redundant. And the value of Cronbach alpha greater than 0.9 leads to redundancy. Redundancy means your respondent have not read these statements, do not understand the statement, and give you the same answer to the every question. Same. So this will lead to redundancy. If your respondent do not understand the statement and they just tick same answer to the same to all the statements, then this Cronbach alpha leads to more than 0.7 and 0.9, and this is called Cronbach alpha. More than 0.9 is known as redundancy. So this is the ideal range of Cronbach alpha. Remember this. Just a illustration. Suppose you are having 3 items, V1, V2, V3. These are 3 statements, V1, V2, V3. And these are the correlation between the statement. The correlation between V1 and V2 is 0.6. The correlation between V1 and V3 is 0.8. So we can calculate the average correlation by taking the average of this. The average correlation is 0.6 plus 0.8 plus 0.7 upon 3, because we are taking the average. Number of statement is also 3. So 3 multiplied by average correlation plus 1 plus and minus 1 into R. So in this way, you can calculate the Cronbach alpha. But we don't need to calculate it manually because software gave you the value of Cronbach alpha, and it is almost mandatory to report the Cronbach alpha in the paper. Even if you are doing pilot survey or you are doing the main analysis. Cronbach alpha is very, very important. You need to report into the paper. After the Cronbach alpha, we have to report the construct validity. And before this, let me insert one more slide. Now, multicollinearity. So multicollinearity, because suddenly this concept is very, very important, because last few days, many scholars asked me to report the multicollinearity. So let me include that also. Multicollinearity means whether the statements, so we are talking about the statements, whether the statements have the normal correlation with other statements or very, very high correlation with other statements. So indicates very high correlation with. So few things which you need to remember, that multicollinearity is a problem which indicates very high correlation with other statements. It is measured by VIF, variance inflation factor. So the full form is variance inflation factor, and VIF should be less than 3. If VIF is more than 3, then it is a problem. And in case if VIF is greater than 3, remove the item. So this is the 4 things which you need to check. Okay, so I will show you how to calculate the multicollinearity problem, because it is a problem which is causing the redundancy in the variables. So if your factor is found to be redundant, means Cronbach alpha is very high, more than 0.9, it means there must be some multicollinearity problem in the statement. So I will show you how we can deal with the multicollinearity problem. Okay. So after analyzing the multicollinearity, especially when Cronbach alpha is more than 0.9, and removing the item, if it is creating problem, then next step is to go for validity. Almost compulsory. So what is validity? Validity is we measure the validity of a scale. A scale means questionnaire. So you have to show that whatever scale you are using in the questionnaire is a valid questionnaire in your context. It may be possible that the questionnaire is already valid. Like for example, service quality questionnaire is a standardized questionnaire. There are many standardized questionnaires proved valid by many researchers, but because you are using the questionnaire for a different respondents in India, country is different, respondents are different, the city is different, maybe the service is different. So you need to prove that my scale is a valid scale. Because if your scale is not a valid scale, it means your conclusions are not valid. So in journal, the validity indicate the truthness, sachai, truth. So if scale is not valid, it means the conclusions are invalid. So it is almost compulsory to report that the scale means questionnaire. Your scale is a valid scale. There are 2 types of validity. One is convergent validity, and second is discriminant validity. Let me tell you the basic definition of both. Convergent validity means whether the construct is significantly represented by the statements and the statement are significantly related to each other. So there are 2 things in convergent validity. Number 1, whether the constructs are significantly represented by the items and the items are significantly related to each other. So both things comes in convergent validity. Convergent validity is measured by 3 measures. One is construct loading. Second is composite reliability. CR stands for composite reliability. AV stands for average variance extracted. So let me tell you the definition of all the 3. Construct loading represents the correlation between the item and the construct. And it is expected that the construct loading of each statement should be greater than 0.7. And it should not be less than 0.5 in any case. Because if there are many items, so some of the items may have small loadings like 0.69, then you can take it, not a problem. But below 0.5 is not allowed. And ideally, they should be greater than 0.7. So there is a confusion basically. What happens when the construct loading of an item is 0.6? So what to do? Whether to drop it or not to drop it? So this is the question which everybody asks. The answer is that if next one, composite reliability. If composite reliability is measured than 0.7, then even if some item is having construct loading of 0.65 or 6, keep it, not a problem. Why? Because average correlation is more than 0.7. So what is CR? CR is the average correlation between the statement, and it should be more than 0.7. So composite reliability is measuring the average correlation between the items. It should be measured than 0.7. It is similar to Cronbach alpha. The third is AVE, average variance extracted. It is similar to the explanatory power of the construct. So AVE is measuring that how much variance of the construct is explained by the variables. Or in another way, we can say how much the items are representing the construct. ये जो items हैं वो अपने construct को कितना explain करनी है, explain. यहाँ पे variance आ रहा है, variance. So how much variance of the construct is explained by the item? So minimum is 50%. So we have three criteria. Construct loading should be greater than 0.7. The composite reliability must be greater than 0.7. Average variance extracted must be greater than 0.5. So these are the three conditions we have to check. After that, we are having the discriminant validity. So discriminant validity, so the conditions are mentioned here in detail, just explaining you before that. There are two measures of discriminant validity: Fornell-Larker criteria and HT-MT ratio. So I will explain you just after explaining all the three. So all the three conditions I mentioned here. Construct loading should be greater than 0.7. Composite reliability must be greater than 0.7. Average variance extracted must be greater than 0.7, 0.5. So these are the three conditions which should be satisfied for a convergent validity. And this analysis is known as confirmatory factor analysis. So this measurement is known as confirmatory factor analysis. So this is a part of CFA. So examining the validity of a construct of a scale is called CFA. After examining the convergent validity, we have to examine the discriminant validity. So what is discriminant validity? Discrimination. Discriminant validity means discrimination. For example, if I show you the photograph of two, let's say, actors, let's say Akshay Kumar and Shah Rukh Khan, can you discriminate between them? Can you identify which is Akshay, which is Shah Rukh? Answer is yes. If I show you the two twins, means suppose there are two twins, you may not differentiate between which is which, right? Which is Ram and which is Shyam. So you cannot discriminate. So discriminate means whether your respondent is able to distinguish between construct A and construct B or construct C. So whether the respondent are able to discriminate the different constructs. If yes, then discriminant validity exists. If not, then discriminant validity not exist. If discriminant validity not exist, it means for your respondent, all constructs are same and similar. This means either your scale is not valid or your respondent is not giving you valid responses. So in both cases, your scale is considered to be invalid. But because we assume that you are very, very sincere in collecting the data, it means your respondent are giving you the true responses. And if discriminant validity is not there, it means your scale is not valid. So discriminant validity must be there. it means your respondent is able to differentiate the different construct. So we measure the discriminant validity by two measures. So these are the formulas for CR and AV. Now, just see this table. This is known as Fornell-Larker criteria. So Fornell-Larker criteria is almost compulsory to report in the thesis and the paper. If you see any paper of SAM, you will find out this table. So this table is known as Fornell-Larker criteria. Just we have to understand this table. The main diagonal, you can see the main diagonal is representing the bold numbers. These bold numbers are the square root of AVE. Like for example, 0.79 is the square root of the AVE of GBL. QD, this 0.739 is the square root of AVE of QD. So the first number in every column is the square root of the AVE. And all the values in the column are representing the correlation. Like for example, in this table, GBL 0.79, this is the square root of the AVE. And the correlation between GBL and QD is 0.69. The correlation between GBL and SA is 0.34. Now the rule is the first value should be highest value in the column. So in every column, the first value should be the highest. Even if you check row-wise, even if you check row-wise, the first value should be the highest in the rows as well as in the columns. This criteria is known as Fornell-Larker criteria. Yeah. So I am representing the ideal value of Fornell-Larker like this. So it is the square root of the AV. It should be greater than all the values. If it is square root of the AV, should be greater than all the values. And if a item is formative or a single item, then AV cannot be calculated. So for a formative or a single item construct, you cannot calculate the AV. So I hope you understand what is the meaning of Fornell-Larker criteria. Even I mentioned that diagonal represent the square root of the average variance extracted, while the other represent the correlations. After that, we are having one more criteria. This criteria is known as hetero-trait mono-trait measure. So let me show this. Now what is hetero-trait and mono-trait? Mono means same, hetero means different. Like suppose in this table, we are having two constructs. This is construct number 1 and this is construct number 2. Construct number 1 is represented by x1, x2, x3. And construct number 2 is measured by x4, x5, x6. Okay. Now we calculate the correlation between all the variables. The correlation between x1 and x2, x1 and x3, x2 and x3. So they are representing the correlation within the construct. Similarly, x4 and x5, x4 and x6, x5 and x6. So this is also correlation within the construct. So correlation within the construct is known as mono-trait. Correlation within the construct is called mono-trait. Now this square bracket is representing the correlation between the construct. Correlation item of one construct with the item of other construct, item of one construct with the item of other construct. So all the correlations are represented as hetero-trait. So there are two types of correlations: correlation within the construct and correlation between the construct. And if I ask you simple common sense, which type of correlation should be very, very high and which type of correlation should be very, very less? So the answer is correlation within the construct should be high. Correlation between two constructs should be less. So we calculate the ratio like this. So in the numerator, the value is Rxy. Rxy means correlation of one construct and correlation of other construct. So it is called hetero upon the Rx into Ry. Rx is the correlation in the X, correlation in the Y. So this ratio is known as hetero trait mono trait. So this ratio should be less than 8.8. So the hetero trait ratio should be less than 0.8. So this is the criteria. So finally, we have to examine the convergent validity by this condition and discriminant validity by two methods. One is Fornell-Larker criteria, and second is the HTMT ratio, hetero trait mono trait ratio, which should be less than 0.8. If all the conditions are met, then it means our scale is a valid scale. So, okay, multicollinearity I show it here. Now, after that, the last assumption is known as common method bias. Common method bias is a almost compulsory nowadays. Even if any paper, if you write a paper or in thesis also, you are required to mention the common method bias. Biasness means biasness can be defined as a tendency of a respondent to answer in an extreme side, either very poor or very good. So if the respondent is having a tendency to give response in either the lower extreme or the higher extreme, this problem is known as biasness. So biasness can be examined by either a single, this Harman single factor method. It is measured in SPSS, and it is also measured in AMOS, which we are not doing today. But single factor method in SPSS, I will show you how to calculate. In along with this common method bias, the another bias is also known as non-response bias. And because many reviewers also ask you that, have you addressed the non-response bias? The non-response bias means, suppose you say that the response rate in my study is 20%. 20% response rate means if you ask to 10 people, only 2 gave you the answer, 8 did not give you the answer. So your response rate is 20%. Now the question is that if those 8 people also gave you the answer, whether your result changes? If yes, then it means your study is suffering from non-response bias. So, like for example, recently somebody asked me, sir, I got selected in that college, should I join? Rather than telling the truth, I keep silent. I did not tell that I simply say that I don't have any idea about that college. So she joined. And after 3 days also quit the job. So the issue is that if I tell the truth, the decision may be different. So sometimes when you are not getting the response from the respondent, it means they are hiding something. In case if they gave you the answer, your result will be different. So this problem is called non-response biasness. Now, how to deal with it? The simple question is that how to deal with it? I have seen many papers where they say that we divided the responses into 2 categories: the early respondents and the late respondents. Early respondents are the people who gave responses without any problem. Many people who denied initially, but we continue to persuade them. We consistently ask them to give the responses. So finally they give the responses. So we call them late respondents. Then we find out the differences between early respondent and late respondent. If difference is significant, it means our results are suffering from non-response bias. And if there is no difference between early respondent and the late respondent, it means there is no non-response bias. The difference between late respondent and early respondent can be analyzed by applying independent sample t-test. So these two type of biasness you have to address in this study. So I will show you how to measure the biasness using Herman single factor method. And yeah, something about bootstrapping. So you know that when you have the actual data, so your data looks like this. It is a non-normal data in 7-point scale or in a scale. So your distributions are not normal. After the bootstrapping, your data will looks like this. So when you apply the bootstrapping procedure, your non-normal data will convert it to the normal data. So it is a normal distribution, it is a bootstrap distribution. So this is the advantage of doing the bootstrapping. It will replace your distribution to normal. And yeah, whenever you calculate the validity, the software also give you the these goodness of fit measures. We are not getting all the goodness of fit measures, but few goodness of fit measures we will get, like SRMR, which should be less than 0.08. NFI should be greater than 0.8. If these two conditions met, SRMR less than 0.08, NFI should be greater than 0.8. Even in some books, it is mentioned that SRMR less than 0.05, NFI should be greater than 0.9, but these are very strict criteria. In general, even if you have NFI 0.8, more than 0.8, and SRMR less than 0.08, it is fine. So there are many papers where I have seen the NFI greater than 0.8 and SRMR less than 0.08, and it is quite accepted. The another measurement of goodness of fit, which I found in a paper, is you can apply the goodness of fit by multiplying average AVE of the constructs multiplied by the R square. So this is another formula which I see in one of the paper, which you can also report. So this is goodness of fit in validity only. And how to report the validity result? So you have to report the validity result in one table. Normally, in this example, you can see we are having 1, 2, 3, 4, 5 construct. These are the construct loadings. Some of the construct loading you can see even in 0.6, 0.665, 0.69. Cronberg alpha is between 0.7 and 0.9. Even 0.1912 is fine, not a problem. But it is lying slightly higher side. So we should try to keep it within 0.9. Composite liability is almost equal to Cronberg alpha. You can see that most of the values are almost same. Average variance expected must be greater than 0.5. Composite liability must be greater than 0.7. So these conditions indicate that the convergent validity exists, and discriminant validity we report it like this. So this table is representing the presence of discriminant validity. You have to report this table in the paper, where first value is indicating the square root of the AV, and the first value should be greater than all other values in the column. So this is must to have condition in the paper. Okay, now so many of you were asking that what is the difference between PLS consistent and consistent simple PLS algorithm and consistent PLS algorithm. Actually, PLS algorithm was initially designed to capture formative construct. Assuming that you don't have reflective construct in the model, you are having the only formative construct or a single item construct. So when you have single item construct or a formative construct in the model, it is always better to go for PLS algorithm. But now they consider the correlation between the items and refine the model. So it means if you are using the reflective construct in the model, simple PLS algorithm will give you the problem. So it is better to go for consistent PLS. So this is the result which I found in the official page of SmartPLS, as well as in some videos, that in case if you are having reflective constructs, it is always better to go for consistent PLS, because simple PLS tend to overestimate the loadings. So this is the reference which I found about the simple PLS algorithm. It is creating a problem when you are using the reflective constructs. So in case if you are using the reflective constructs, it is better to go for consistent PLS algorithm. So normal PLS algorithm is used for formative scales, whereas consistent PLS algorithm is used for reflective scales. So this is the basic conclusion about the difference between PLS algorithm and the consistent PLS algorithm. Now, after discussing with the theory, now I'm showing you how to calculate the validity and all these things in SmartPLS. Opening the software. So yesterday we have created a project for behavioral intention. So let's do that. So we will go for day 2. And this is a SAM model. So when you go to the SAM model, the picture will come. Now you have to make this diagram. And after making the diagram, now we are interested to go for the validity analysis. First of all, go to the calculate. And you can see two options, PLS model algorithm, which is basically created for formative and single order constructs, single item constructs. However, because all the constructs are reflective in nature in this model, so it is better to go for consistent PLS algorithm. So I click on consistent PLS algorithm, do nothing, just click on start calculation. And now all the result will come automatically. So these are the results. So first of all, we have to check the construct reliability and validity. You can see the cursor. If I click on this, the Cronbach alpha is lying between 0.7 and 0.9, not a problem. Composite reliability is greater than 0.7, not a problem. Composite reliability is, there are two composite reliability in this, row A, row C. So we have to check the first one, or both are almost coming to the similar. Average variance extracted is must be more than 0.5. However, in this case, we are having two problems like 0.482 and 0.47. So in two cases, we are having a problem. So whenever your AVE is less than 0.5, the software will show you the problem. So there are two problems in this. And after that, we can go for the discriminant validity. Discriminant validity is measured by Fornell-Larker criteria. So the first value, 7, 9, should be greater than all other. 6, 9 should be greater than all other. Yeah. 7, 9 should be greater than all other. This should be greater than all other. So you can see that we are having all values satisfied, not a problem. Even this value is more than this. Yeah. So we don't have any problem in this. All results are fine. Then after looking at the Fornell-Larker criteria, now you go for heterotrait monotrait. all green indicating the problem, no problem. So you can see that we don't have any problem. And by looking at the bar chart, you see that all these are green. Not even a single bar is red. If you see any red bar, then it is a problem, but here we don't have any problem. So convergent validity wise, we don't have any problem. And in this way, we can check the discriminant validity by looking at the Fornell-Lurker criteria, where first value should be greater than all other, and heterotrait, monotrait, where all values should be less than 0.8, not a problem. And you can see that now we can go for collinearity statistics. Collinearity statistics. And we go for outer model. There are two collinearity statistics, inner model and outer model. So we have to check only for outer model, not for inner model. Now all the values, you can see, all the values are less than 3. All the values are less than 3. So it means our data is free from multicollinearity problem. All the values of all the items are found to be less than 3. So there is no problem of multicollinearity in the data. And so we are having all the values, and finally we have to go for model fitness. In model fitness, you can see we are having the model fitness. SRMR is less than 0.05, 0.08, good. NFI is more than 0.8, so they are both are acceptable in nature. So if both are acceptable, it means our validity model is fine, not a problem. So we have checked the reliability, validity, and multicollinearity from this table. So just to repeat, first of all, we have to go for construct reliability and validity. Check this table. Then go to discriminant validity, where we have seen Fornell-Lurker criteria, HTMT ratio. So these two values are representing the discriminant validity. Then we go to the collinearity diagnostics in outer model. All the values are less than 3. Then we go to the model fit, SRMR and NFI. These two values are in a line. So these 4 things you have to check from here. And after that, if you want to see the normality, you just go to the data. If you click on the data, so I just click on the data. If you click on the data, you can check the skewness and kurtosis. Skewness and kurtosis. So all the values are found to be like, for example, we have problem in this. These two values are more than 1, having a problem. And similarly, this value is also more than 1, problem. Yeah. Gender, marital status, and income, we have not checked. We should not check the kurtosis of these. Kurtosis and skewness should be checked only for the interval scale, not for a nominal scale. So kurtosis and skewness representing the normal distribution, we can check from this table. And finally, in the last, we have to check the biasness. So for biasness, we can go for the SPSS file. And from there, we can check whether the data is biased or not. I'm just showing you a simple test. This is my behavioral intention in the data. I have to open in SPSS. So first of all, I am opening the SPSS. In SPSS, I will import the data and will check the biasness of the results by Herman single factor method. So this is a blank spaces. So we can import the data from CSV and find out the folder. So this is SmartPLS 4 day 1 to 3. Yeah, this is the data. So you can directly import the file like this. And after this, go to analyze, dimension reduction, factor, take all the variables in the file, only the scale variables, not the demographics. Take to the variables, go to extraction. We have to give a condition that only one factor should be extracted. We have to give a condition that only one factor should be extracted. Continue. And do nothing, just click OK. So you will get this table. So this value in table total variance explained, if this value is less than 50%, it means your data is free from biasness. I repeat, if this value loading cumulative is less than 50%, it means your data is free from common method bias. So in this way, we can check all the assumptions, and you know that all the assumptions are almost compulsory to check. If any of the assumptions is not satisfying, it means you have a problem. So this session is focusing on the assumption testing, and I think I covered each and every aspect of the assumption testing. So in case of any problem, we can discuss in the discussion section. So that's it for today's session. And anything, if you want to repeat, then we can do in this discussion.